So this is an old project. Make sure, well, to get the exact same number, and make sure you have the same specification on the variables. So I have, for this data set, I have accepted every variable, including the one variable that probably has some issue with, the area code. But for now, I'm including it just for demonstration. Target is the churn, phone is the ID, and there's only one state, one nominal variable, but there are many levels in it. Phone is nominal, but it's ID. And there are a couple binary, as you know, and the rest is interval. A caution, though, here, that when you do the homework, you need to make a decision about, which variables that you need to exclude. And one thing to consider is the covariance, the correlation between the variables. If you remember, during one of the homework, you answered why you didn't have to do, you didn't have to explore some of the variables because they are collinear with some of the other variables. With the perfect collinearity, it wouldn't make sense to include both in the same neural network analysis. It may cause big trouble to the model. It will make the model unstable in the gradient descent, because the two variables contain exact same information. Essentially, it creates unstable optimization process. But for this example here, I'm demonstrating how this will map to the number of input neurons if I include everything. The model itself will not exclude those variables with trouble. So you would, as the analyst, you would have to, do the task and exclude those variables. So if I have this setting, and normally you would have a partition still. Where's a sample? So let me follow that after transform. Transform probably did some log transformation, which won't change the input neurons. And this wouldn't also, this will not alter the result about neural networks in terms of number of neurons. So I want to keep the default, and then it's a neural network. So now let me update that path. And take a look at the variables. Well, it's hard to see. So row on. So ID is already excluded by default. That's great. So based on this chart, you can use the first method to sort of figure out how many input neurons would there be. There are 3 binary and a bunch of interval. All of these are fine. So you would simply count the number of variables here. Let's see, how many do we have? But excluding the target, 1, 2. So I have 19. I have 19 binary. interval. One nominal. Do you have the same result? Do you have the same result with me? 19 binary slash interval variables. Do you? So hopefully, so double check with me if you have the same result. I need to figure out how many levels are in state. Typically 50, but just to double check. One way you can do that is in Stat Explore. It shows you the basic information about each variables. So for state, where is the state? State has 51 levels of different levels. So you would count 51 in this case. So then it will become a simple addition of the two numbers, and should be 70 input neurons in this case. If you have rejected some of the variables and made some changes to the nominal variables, like rebinning or combine the beans or things like that, it will be more complicated. You will need to find a way to, trace all the changes and figure out how many input neurons go into the neural network. So that's one way. That's the first way. And the second way is to specify the neural network model and then look at the results and backtrace. So hit the wrong button. To make it easier, I'll specify 5 layers. I mean 5 units, 5 hidden units, because it's easier to calculate in that way. And I'll run it. So I skipped a lot of things I should have done. Right? I should examine the model selections. I need to look at this and that. But for this example, I'm only demonstrating the neurons. Okay. All right. The results table include a lot of informations, including the sort of the parameter rates of the best model after it has gone through the selection process. There are 2 sections that are quite similar, but they display different statistics about the same parameters. So you can look at both table. This table shows 300 something rows, 350 rows, 350 coefficients basically, and this table has the same number, but they show different stats. You can use either table. The information that you need is basically the total number, and you also need to look at the labels here. But in that case, both tables will be similar, right? So the information that you need is look at those parameters with the suffix, with hidden layer number. We have 5, so we'll have 5 different kind of suffix, and make sure you don't count the bias. Each hidden neuron has a bias term, which is not associated with any input neuron, right? It's a neuron of itself, so don't count it. Going through the list, you have the interval variables at first. So it shows the interval variables, the coefficients of those interval inputs with each of the hidden unit. Now I have 5 hidden units, so you should expect to see hidden layer or hidden layer 1, hidden layer first node, and starting here it's second node, third node, fourth node, and fifth node, and until here. That's the end of the interval variables. And starting here, you have the binary and nominal variables. Binary first. Let's see. So 2 binary linked with the first hidden unit, and the second unit, third unit, and fifth unit. And down below, it's the state. It's the giant nominal variable has 51 levels. So you expect to see 51 coefficients per each unit, per each hidden unit, and then it rotates and repeats, right? So toward the end, you will see 2 new things. Have the bias associated with each of the hidden unit, and you also have a bias associated with the output unit, which is also a hidden unit. And then you'll see the coefficient of the hidden unit linking to the output unit. So that's also that's not because of the input neuron, but because of the hidden layers. So the information that you need here is mostly toward the top, right? You can scroll all the way until you have the bias. So you have 345. 345 divided by 5. That should be the answer. 69. Off by 1. Is that off by 1? Let's see. Maybe because of the state. 1 level is left out, probably. Let's see. Or see if we have the same number for the intervals. Up until now, that's the interval. So I have 17 plus 2 binary. So I have 19 binary / interval. So that's correct. The only thing different is the state. Let's see. It's 95. 146 minus 95 is 51. That should be right. Interesting. Okay. 145 minus 95. That's 50. Okay, yeah, I should use this one. So 50 different state levels are counted. I probably have to revise that for any nominal variable that has k levels, only k minus 1 is included because of the collinearity issue. I wasn't particularly clear on that point, but these you would rather trust these results than the other hand calculation. and that would be the case for regression models, that you would leave 1 level out. Otherwise, you will create a variable with levels that are collinear with each other. So that's the case for regression. I wasn't very sure about neural networks, but seems to be the same case, right? So then in that case, both ways, we need to update that method, but then both method leads to the same result. I hope it's clear now. Right. From the results, it's easier to get the correct result. Question?
Professor, your conclusion on collinearity, I don't think I understood that.
So that's my best guess. In terms of regression, you can almost, in regression, maybe easier to understand. Let's say you have a gender variable that's binary. You have two levels, males and females, let's say. And you would typically only include one of them, because knowing one means you know whether or not the value of the other is 0 or 1, right? If you include both levels of binary variables, then those two predict each other, becomes linear. In this case, regression will reject one of them by default, right? So that's the case with regression. It can be seen as the same way in neural networks. All right. I hope this will be helpful for the homework. All right. So here comes the exciting part: evaluations. This is mostly about types of errors. Let me turn it off. Continue with the recording. All right. So we'll look at the best decision tree, best classification tree. As you can see, I've done quite a few things here. So last week I trained a neural network model based on the entire data set, and it's not performing very well. It's as poorly as the maximal tree, I think. No, it's better than the maximal tree, but it's worse than the stepwise regression. So we're trying to beat that stepwise regression. I tried various things, didn't work. I get very close to that, but just shy just a little bit. I can talk more about it next time if we have time. But here we're doing this best classification tree. So currently there are no decision weights here. Let me double check. So there's a decision table. Where is it? Commons. Data source. Somewhere. Decisions. Decision weights are equal. Decision 1 is typically the primary decision, is the decision that you will do for positive outcome. So in this case, if the person is a predicted donor, you will solicit, right? So decision 1 is to solicit in this case. So currently, let's see. So this model comparison is using misclassification as the criteria to compare models, and I can leave it there, and then I will modify the data set, modify the decisions, and leave this comparison criteria the same. It will keep display the same result. I will train another classification model that takes into account the decision weights, and then we can compare the performance of that new classification tree with this old tree. So I think first thing to do is to to configure the profit matrix. It's on 35, page 35. Now, recall that you need to specify the expected profit from a donor, right? In the case of a positive, true positive, right? You'll specify how much profit you expect from this person. So that's the average amount of donation minus the mailage, postage. But where do you get the expected donation amount? Right? If you recall, there's another target in the data set. It's the donation amount. It's only for those who donated, right? So you can basically do a calculation of the average donation amount of that new variable without considering the missing values. The missing values are those who didn't donate. So naturally it's 0 and don't have to be considered. So in this case, there's a mechanism to do it even after you have started the project, right? So the first thing is to customize the decision. I think with the prior probabilities, it also needs to be updated. But here it didn't talk about that. With donations, we know that there's only 5% people on average, of various cases, 5% people will donate, and 95% people will not donate, even if you ask. So with the adjusted prior, it would be worthwhile to change that. Okay. So decision 1 is to solicit. Decision 2 is to ignore. It's to not solicit. And let's see, decision weights. So both of these should be 0 because you won't have a cost or benefit if you ignore. And things change when you decide to solicit. If you solicit but the outcome is 0, then the benefit would be the postage amount, which is negative 0.86. Here, the expected benefit of soliciting a person who's a donor would be the average donation amount minus the postage, but we don't know the average amount of donation, so we need to look up. So for now, you can save the progress, but come back later. Here, what it used is it created another Stat Explorer, but we already have one, so we can look at the Stat Explorer results. We're looking for, there's some change that need to be made. I think that's why. We'll use a different, a different Stat Explorer. And be sure that if you want to have a fair estimate of the average of a variable, hopefully you create that node before data partition, because when you have the data partition, you have fewer data that you look at, right? It's a subset. Even if it's a random subset, it's not perfectly random. So what may give you a biased value. So it's better to use the original data set. And in here, because target D, which is the donation amount, was rejected, so you need to find a way to take it back and be able to see the results out there. So that's why for this particular node, in the variables, you will, even though it's rejected, you will change it back to yes, so it will give you results over there. You can even, reject everything else because those are not the purpose. But here, I'm just going to leave them there. So we're looking for the average, the mean of target D. Should be under numeric variables. The mean is $15.62. It's the same as what the tutorial is saying, so we'll simply use their result. So what it does here, it does have 4,000 missing values, or those cases that didn't donate, but with non-missing values, you have the mean of $15 on average. A donor would donate $15, so you expect that would be a good guess for any potential customer. So, and minus the postage, it will come down to $14 something. So we will go back to decisions and modify that. So it's 13, 14. And that's good. Okay, now this is updated on the decision weights. It won't affect this node. It won't affect this node. It might affect this decision tree model. Here, it won't affect the growing part of the tree, because the growth of the tree relies on the basically the classification part, the 0 and 1 outcome, and it uses a log p, which is entropy close to. So it doesn't take into account the decision weights, and the selection was with misclassification. So if this setting doesn't change, then the best model selected won't change, right? Because it's not using the decision weights. And I'm going to create another tree. Let's see. And connect data partition with that to be able to compare the two. I would say best profit tree. And while keeping things the same, the only thing I need to change is decision, basically. Decision considers the profit and its decision weights. Not much else, I think. And let's compare them using the profit. Where for assessment, we be sure to specify average profit loss is profit loss per case. On the validation set. Right. So now you can run. And let's run this because I changed the data set just to make sure we have a fair comparison. Neural network. This one has some problem. And I need to compare this one over here about misclassification rate. Let's do that again. Takes a long time. A lot of neural networks are having some problem. I'm not sure why. Yeah. Anyway, so let me create a different comparison here. This is decision. On validation. Okay. This is misclassification and that. Let's move these out. So it comes down to these two comparisons, right? Oh, so So best model. Oh yeah, that works. And here. All right, it's finished. Let's see. So it's quite clear as expected. This tree with best classification tree, the criteria is misclassification. So it did all the training and the selections. The 0.5. Looks weird. Anyway, so I was expecting the misclassification tree to rank higher based on misclassification. I wouldn't expect these numbers, so it needs time to look into. The error rate of the misclassification tree is supposed to be lower and should be ranked higher because it's searching for the tree that performs the best on misclassification rate. So on this one, it's kind of expected, but requires more investigation. On the other side, I would expect that the profit tree to rank higher still. So it didn't change the result. There's something going on here in the model. It needs time to and there were some errors with the neural networks. So definitely, will require some more time to go back and make sure the properties are right. But this would, I would say, as the project gets complex, as you change things around, this would be something that would happen in your project. So be prepared and go back and diagnose, and you can. Sometimes you can't explain why things are weird. The backup solution is that you keep notes of that node and settings, delete it, and bring a new one in, replicate the setting, and run it again. And a lot of times that solves the problem, but just can't be explained. Let's see. So, right, adjusting. So that's that part. Right. And neural networks that I talked about this, a deeper neural network, it's capturing the features that are more complex and nonlinear, and so using the facial recognition as an example. The deeper the network goes in, it recognizes the eye and nose and facial features, more complete features, as with where the shallow layers are picking up the edges. Okay, so these are the teams. If you want to discuss the team formation, talk to me after the class. Let's see. Just a reminder: when your team submit the deliverables, the project, only one of you, please, submit the project. Otherwise, they create inconsistencies. I would ask the name in bold to please submit the project. I will only grade the project under your name for your team. Model deployment. Seems like we have a couple more minutes. So Suppose after you have trained all the models, you have compared them, you have diagnosed the models, then you need to predict a new data set, let's say. If this is in practice, if you're deploying the system to practice, then you'll have ongoing new cases, maybe periodically, every month, you have a data set of how many cases that you need to predict. And this is different from the training set, right? So Sass treat them slightly different, as a slightly different type of data set. You will do something similar, but other things different. One distinctive difference is that you don't have the target variable, because these are new cases, right? You don't need a target variable there, but you need to make sure all the other inputs have the same levels that you specified for the training set. So it's in the tutorial. We'll just do a quick demo and what are involved here. So let's see. I'll use an example data set because I don't have a test set. I don't have a new set for the churn problem. So I'll use any data set to demonstrate for the purpose. I think it's under utility or application. So you will use a Sass node to write some programs to make the, let's see, or you don't have to. I think, let's see, run model. Where is it? Save data. Let's see. Score. Score is here. So after model comparison, let's use this one. You'll bring a score and you'll connect the model comparison, or you can connect a particular model. That's your choice. Connecting model comparison with the score will use the selected model only. Right? You have a list of models, and model comparison will indicate which model is selected as the best model, right? And it will only feed the best model to downstream nodes. So that's good, and there's not much that you need to specify here. See? But also you need another data set. So you need to create a score data set. Let's see. So I do have a score data set. Let's say score. Bankruptcy. Well, let's say I use this one for demonstration purpose. Most of the things will be similar, unless you won't have these, columns by nature. So for now, I'm going to reject it. And make sure you have the same levels and same row for all the other variables as with the training set. Most of the things will be similar, other than that. For here, the step will be different. you need to designate a score data set to be used for scoring purposes. And basically that's it. Then you'll bring in the score data set and also feed into the score node. And that's basically it. You make the prediction. There's some properties that you can change, but the basic results will be similar. The result of the scoring node will be a new data set with several new columns. You have confidence, you have prediction result, and several other metrics. After the scoring is done, you can export the data set. For the homework and for homework and test, you need to export the data set and upload it to Blackboard, right? So you would do that after you have run a score and save the data set. One way to save the data set is use the save data node. You can choose to save. You can designate a partition to save. In this case, you would like to save the scored data set, right? That's one way. Another way is to use Sass code, which the tutorial talks about. I'll show you just a little bit. Let's see. So there's a Sass code where you can start to program a little bit about Sass. You'll connect the score set with the Sass code. And you'll go into the code editor. It takes a little bit time for it to come up. Right. So here, the job is to specify which table to export and export to where. So just one snippet of Sass code to do one task. And the tutorial provides a template, but don't type literally everything, and you need to learn a little bit about Sass syntax rules. So let me type and you'll start noticing some differences. So you see the color coding of the syntax. Those are keywords, and you can't change them. You can't misspell them. They won't work if misspelled. And the dot symbol is for library. The portion before the dot is the library. So I have my library I don't remember if it's MyLib, but I think it's MyLib. So you will use your own library name, otherwise it won't work. And you expect to find the exported data in that library. And this is the new dataset name. You can make anything that you want and just look for that name. This part would be the also the system designated name. You have to use that. And it has an ampersand before it, means a hidden system data set that has this name. So you're looking to copy the score data set from the system into this new data set in this location library, and that's it. After that, don't forget to save and close it. Then after running the Sass code node, it's running that line. I haven't run the score, so I can't run this, but won't be much trick beyond this point. So that's one way. All right. Any other question? So we have finished supervised learning by this point. So you can start exploring the project, right? And the project is a supervised learning project. So you'll train supervised learning models to try to predict the sales price of houses. For the next 2 weeks, we'll talk about unsupervised learning, clustering, and association rules. And after that, it's project time and, miscellaneous diagnostics and teamwork. All right, that's it.
Are you ready for project management hours?